Hi, my name is Dr. Brad Bailey, and I'm a program scientist at NASA headquarters in the Exploration Science Strategy and Integration Office as part of the Science Mission Directorate. And I'm here to talk to you today about why the moon. Why are we going back to the moon? How are we going back to the moon with robots and with humans? And what is the overall benefit from a scientific exploration and technology demonstration perspective? So the moon has actually been thought about for quite some time. And the nation's top scientists and strategists have identified the immense scientific potential, economic opportunities, and national security interests associated with getting back to the lunar surface. Below, you see quotes from 3 different studies that have spanned the last 30 years. And in them, they all say that the scientific potential, economic opportunities, and national security interests are of utmost importance. But the last one on the Space Policy Directive 1 from 2017 has told us, lead an innovative and sustainable program of exploration with commercial and international partners to bring back to Earth new knowledge and opportunities. The United States will lead the return of humans to the moon for long-term exploration and utilization. And that is the driving force behind why we're returning to the moon now. So we'll talk about the science associated with that here in a little bit. However, the moon itself actually has a wide variety of extra benefits that come back from the science and technology that's been demonstrated on the surface. And that feeds forward into the everyday lives of people here on Earth. The moon is our gateway to the solar system. It's the place where we can learn to live and operate in the harsh environments of the lunar surface, including radiation, partial gravity, and how do robots and humans work together in order to do scientific exploration. The moon is close enough to be achievable with reasonably routine access, but it's also difficult enough that we can advance those technologies that I just mentioned. It's also here on the moon where we can realize that we are indeed a spacefaring species. And with enough infrastructure and a genuine foothold on the moon, that is critical for how we are going to expand outward into our solar system. Exploration actually enables science, where humans on the lunar surface for extended periods of time, actually together with supporting infrastructure, yields unique scientific opportunities. For example, an Artemis base station will provide logistics, and a reusable infrastructure will allow access to locations of scientific interest on the moon. We are also working towards a robust communication and navigation network, which is critical for our astronauts leaving the relative safety of the landing site and moving out to complete further lunar exploration. Decadal level science can also be achieved in the region around the poles of the moon, which is accessible by unpressurized lunar terrain vehicles as well as pressurized rovers. And other fundamental science questions will require the ability to do regional scale fieldwork, and eventually we have the goal of global access across the entire surface of the moon. So we are undertaking new science and exploration initiatives. Humans actually enable the careful collection, curation, and return of new geologic samples that could revolutionize our understanding of how planetary bodies form and evolve. One of the lasting legacies of the Apollo missions to the lunar surface are actually our wealth of samples that were returned from the astronauts. These samples continue to this day to yield new discoveries and again teach us how planetary bodies form and evolve. Exploration of the lunar poles permit the return of lunar highland samples from terrain that's geologically and geochemically different from those explored during Apollo. Regional exploration of the South Pole Aitken Basin could yield samples of the lunar mantle, and these samples can provide new information on processes that have shaped the terrestrial planets, such as the global magma ocean hypothesis, as well as learning how the terrestrial planets formed and evolved. A polar location enables the emplacement of a far-side radio array that can leverage this unique radio-quiet region to begin addressing cosmological questions from the beginning of the universe and when stars first started turning on. The polar regions also support polar ice. The extraction and return of polar ice samples will provide details not only on the origin and evolution from these deposits, but potentially the building blocks of life. The collection and return of these deposits require human and robotic synergistic exploration. Cold traps on the lunar poles may retain evidence of prebiotic chemicals delivered from asteroidal and cometary material, which has astrobiological implications on the origin of life here on Earth. Polar ice may also contain volatiles and material left over from early in the moon's history, and that may inform us on the source of Earth's water and surface chemistry. And exploring the nature of the volatiles found on the polar regions of the moon will yield overall important science data that we may be able to use for human exploration and humans existing and living on the surface. If we have a sustainable human presence on the moon, we need to learn to live off the land. Human exploration of the solar system will always be constrained if we have to bring everything from the Earth that we would need for living on the surface of the moon and the ultimate return journey. Polar ice and volatile deposits represent low-hanging fruit, where water is both a life support consumable and a transportation propellant. You can take the hydrogen and oxygen associated with water and split it apart into hydrogen and oxygen fuel that we can use for rockets in order to come back to Earth. You can also take that hydrogen and oxygen and use it in both its native water form for drinking and for plants, growing plants on the surface, but also you can use the oxygen for breathable oxygen by the astronauts. Our initial goal could be to make the propellant we would use for regional and global lunar exploration. And that can be done by fueling up rockets where we could hop from one place to another to do scientific exploration and then hop back to our sustainable base near the poles. Human exploration will allow us to prospect for this resource in a more comprehensive manner than purely robotic prospecting or that can be done from orbit. So we are currently working on developing human and robotic synergistic exploration, where we could put prospecting instruments on the lunar terrain vehicle, and as the crew conducts their scientific exploration around the margins of permanently shadowed regions, we are continually monitoring the subsurface, looking for deposits of volatiles and ice. We are also working with the commercial sector. American companies have been contracted to deliver science and technology to the lunar surface through the Commercial Lunar Payload Services Initiative. Once information on the nature of the volatile deposits is obtained that shows these reservoirs are present, extraction can be conducted by the commercial sector, for example, through terrestrial mining. The government would become the anchor customer for the processed resources. And the goal would be for NASA to not only be the customer long-term, but first we would need to grow this market. 100 years from now, if we are exploring the solar system with people, we will be using the moon and someone will be making a profit. And we want that someone to be our US companies. There is, of course, a strategic value to lunar exploration. The moon is the ultimate high ground, and the US relies on multiple assets in Earth orbit for situational awareness. The moon is outside of Earth's deep gravity well, and it's actually easier to get to Earth orbit from the surface of the moon instead of the surface of the Earth. The lunar poles are enabling because of the existence of location of near permanent sunlight and the craters of permanent shadow containing water ice deposits. However, there are a finite number of such locations, and thus they represent finite resources. So we must make use of them strategically. What are our near-term needs? How are we going to go forward and make the exploration of lunar surface possible? We do need that communication and navigation network, which will allow us to explore wherever we need to go, not only on the near side where you can have direct to Earth communications, but on the lunar far side where you can only get communications with Earth through some sort of communications relay. We are working on a campaign of rovers. The moon is a big place requiring a systematic exploration campaign. We're working on developing survive the night capabilities, as much of the science we want to achieve requires collection of data over long periods. And the lunar night is very cold to where robotic and instruments that would be operating on the surface it makes it more difficult to survive. A robotic sample return is required to bring back high-value samples from regions that will not be visited by humans in the near term. And so with that, I hope that you now have a better understanding of where we are going on the moon, why we're going, and what the overall benefit to it is. And I hope that I can see you all on the moon in the not too distant future. Godspeed.